numbers, and that segment is, I would say, factorization, factors, which will include questions on number of factors, sum of factors. Alright, now let's see. Let's start with an example. Find, if the question is find number of factors of 100. One way is that you can create actually all the possible pairs which are factors of 100, like 100 can be written as 1 into 100, or 2 into 50, or 4 into 25, or 5 into 20, or 10 into 10. So if you count the number of factors, 1, 2, 3, 4, 5, 6, 7, 8. Now these two are same, so we count only 1. So when we count, we have to take only 1 out of these two. So total 8 and 1, 9 factors. Now 100 is a very small number, so we could actually count the actual possible factors. Let's take another example, 72. So if you count the number of factors of 72, we can take them as 1 into 72, 2 into 36, 3 into 24, 4 into 18, 5 will not be a factor of 72, 6 into 12, 7 will not be a factor, 8 into 9. After this it will repeat, so you don't need to go further. Okay, so total how many factors? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Or you can also do it like this, how many pairs? So 1, 2, 3, 4, 5, 6. 6 pairs, and in each pair there are 2 factors. So total 12 factors. Once again, the number is very small, so we could actually count the number of factors. But if the number is very large, say for example, how many factors are there for 84,000? If the number is very big, then what should we do? For that we have methods. Now to understand that method, first let's try to understand the meaning of factorization. When I say factorization, it means we have to break the given number as a product of its prime factors. Okay, so for example, if I say 6, it can be 2 into 3. If it is 10, we can break it as 2 into 5. If it is 12, it can be broken as 2 into 2 into 3. Now, one thing that we need to understand, if there is a particular prime number which is appearing more than once, then mention them as powers. For example, 2 is coming twice, so we can say it is 2 to the power 2 into 3. Now, if there is only one 3, that means it is 3 to the power 1. 6 can be written as 2 to the power 1 into 3 to the power 1. 10 can be written as 2 to the power 1 into 5 to the power 1. Let's say for example 24. It is 8 into 3. Hence it is 2 into 2 into 2 into 3. Now this will be written as 2 to the power 3 into 3 to the power 1. 100. 100 is what? It is 10 into 10. It is 100. 10 into 10. So this can be written as 2 into 5 into 2 into 5, which is further written as 2 square into 5 square. 72. 72 can be written as 8 into 9. Hence it is 2 cubed into 3 square. So as much as you memorize or remember the tables, it will be easier. Right? Now there are some people who would also be comfortable. There is something called danda method. For example, if I have to factorize 72, so I draw one danda like this and another one like this. And then you go on taking out some factors. Now, taking out factors means by division. For example, if I take out 2 from here, divide this number by 2 and write the quotient here, 36. Then again, 36 can be further factorized. So 2 you take out and you divide 36 by 2, you get 18. Again, suppose you want to take out 2, divide 18 by 2, you get 9. Then divide 9 by 3. So, jisse bhi divisible hoga, you take out that factor. Okay, so it is divisible by 3, so take out 3. Now here 3. Again, take out 3, it will be 1. So continue this process till the time you get 1. Whatever you have got here, multiply all of them, that will be the factorized form of 72. So for example, 72 can be written as 2 into 2 into 2 into 3 into 3. So 2 into 2 into 2 into 3 into 3. So this is 2 to the power 3 into 3 to the power 2. I'm sure you can recall that you have done this in lower standards, right? So the numbers can be factorized like this. Okay, now how does it translate to find the number of factors? We'll see that in some time. So the first thing that we need to understand is how to factorize a number. Let's take some more numbers like 144. So we know it is 12 square, which is 12 into 12. So I say that those who are not comfortable with tables or those who do not remember squares, they can use this method, but slowly and gradually you have to try and practice that you get into, you remove this middle process or middle steps. The faster you get to the last step, it will be easier for the next part of the question. Understand that to find number of factors will only be a small part of the question, right? So you can't spend so much time on this. Try and see that you do as fast as possible. Now 12 into 12, it is 2 square into 3, 2 square into 3. So total will be, so ek bar I'll write it 2 square into 3 into 2 square into 3. After combination, it will be 2 to the power 4 into 3 to the power 2. Make sure that if a prime number is appearing more than once, it has to be mentioned only as the power. You cannot mention them separately. So all the appearances of a particular prime number should be mentioned as the total power of that. So for example, 2 appears 4 times, it has to be written as 2 to the power 4. For example, 3 appears 2 times, so it has to be written as 3 to the power 2. Or let's say 120. Now 120 is 12 into 10. So it can be further written as 2 square into 3, 2 into 5. So total 2, how many times 2 is coming? 2 times here, 1 time here. So total 3 times. So 2 cube. 3 was only in this one, so 3 to the power 1. 5 only in this one, so it is 5 to the power 1. Okay, so you can further try. Let's take some more numbers. I'll give you some numbers. Let's say 360. Right now I'm just asking you to write the factorized form of these numbers. 360, 720, then we have 576, 1000, 900. Just factorize all of these numbers. Okay. Now 360 is just 120 3 times. So if you have already done 120, it is 2 cube into 3 to the power 1 into 5 to the power 1. So 360 will become 2 to the power 3 into 3 to the power 2, because we just have to multiply this whole thing by 3. So 3 ka power will increase by 1 into 5 to the power 1. Other things will remain same. If you don't know 360, just multiply it by 2 and you get 720. But yeah, I would suggest that you do each and every number on its own as an independent question. So for example, 720. Now it is 72 into 10. 72 can be written as 8 into 9 into 10. Now 2 cube here and 2 here. So it is 2 to the power 4 into 9 is 3 to the power 2 into 5, that is 5 to the power 1. Okay, 576. If you remember, it is 24 square. Now 24 itself is 8 into 3 or 2 cube into 3 whole square of this number. So it is 2 to the power 6 into 3 to the power 2. 1000, it is 10 into 10 into 10. So 2 into 5, 2 into 5, 2 into 5. So 2 to the power 3, 5 to the power 3. You can see that in every number, there may be a different process, but it depends how good you are with tables, squares, cubes, and so many other things. Just understand that for us, the most important numbers are, below 1000. Up to 1000 are the other numbers which are very, very important for us. Even in that, if you look at the questions or past questions, multiples of 6, multiples of 12, 30, these are the numbers which are very important for us. Okay. Now 900 is 9 into 10 into 10, or you can also say it is 30 square. So this can be written as 3 square or 2 square into 3 square into 5 square. So this is the factorized form of numbers. So take some time, just repeat, revise what you have done till now. Now once we have done the factorization part, now we can find the number of factors. For example, this 84,000, you can also factorize this number. So if you factorize this, it is 84 into 10 into 10 into 10. Every 0 will translate into a 10. So 84 is 12 into 7. So I'll write once 12 into 7. Then 10 cube. Now see, from 10 cube, from each 10 you'll get a 2. From 12 you'll get 2 square. So total 2 how many times? 5 times. So 2 raised to 5. Into 3 only once from here, 3 raised to 1. Into 5 only here, that is 10. So 10 cube here, so 5 cube. Into 7 raised to the power 1. So 84,000 can be factorized as 2 to the power 5 into 3 to the power 1 into 5 to the power 3 into 7 to the power 1. To find number of factors, we need to understand the method of or the process of formation of a factor. Okay, let's see. We'll take an example again, 72. Now what was the factorized form of 72? 72 was 2 cube into 3 square. The prime factorized form of 72 is 2 cube and 3 square. From here, what do we know? From here we know that 72 or the factors of 72 can be created only by 2 and 3. Even in that, how many 2's are there? There are 3 2's, and those 3 2's as powers of 2 can be written as 2 to the power 1 or 2 to the power 2 or 2 to the power 3. Now what I'm trying to say here is, if 2 cube is already available here, that means to create a factor of 72, I can use all the 3 2's, that is 2 cube, or out of these 3 2's, I can use 2 2's, so that is 2 square, or if I can use only 1 2, that is 2 to the power 1, or there may be a situation where I do not use a 2, so in terms of power of 2, I'll say it is 2 raised to the power 0, right? Can I use 2 to the power 4? To create a factor of 72, can I use 2 to the power 4? Think about it. No, we cannot, because 72, it has total 2 cube. The highest power of 2 in 72 is 2 cube. So we cannot go beyond 2 cube. We cannot take 2 raised to the power 4. That means the powers of 2 that can be used to create a factor of 72 are 2 to the power 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2 and 2 raised to the power 3. That's it. Similarly, powers of 3 which can be used to create a factor of 72. Let's see. 3 square is there. So 3 square can be used, or a lesser power 3 to the power 1 can be used, or a lesser power 3 to the power 0 can be used. We don't have to go into the fraction, so we cannot take negative parts, right? So what I'm trying to say here is, the summary is, if the power is given, we can use that power of the prime factor or any lesser power of that prime factor up to what? Up to the lowest power 0, right? Before going ahead, I'll take another example. If I say 144, now 144, if you factorize, it was 2 raised to the power 4 into 3 square. That means the powers, the available powers of 2 which can be used to create a factor of 144 are 2 raised to the power 0, 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, and that's it. Similarly, the powers of 3 which can be used, 3 raised to the power 0, 3 raised to the power 1, 3 raised to the power 2. Alright? If it is 27,000, that is 3 into 3 into 3, 10 into 10 into 10. So 30 cube. So it is 2 cube into 3 cube into 5 cube. So the powers of 5 that are useful are 5 to the power 0, 5 to the power 1, 5 to the power 2, 5 to the power 3. Similarly, the powers of 3 which can be used, 3 to the power 0, 3 to the power 1, 3 to the power 2, 3 to the power 3. The powers of 2 which can be used, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. Alright, so these are all powers of the prime factors which can be used to create a factor of the given numbers. Okay, now we come back to 72 again. Now, how do we create a factor of 72? We just need to take any one of these and any one of these and multiply. You know, like these. Let's say this one and this one. So if you multiply these two, you'll get a factor of 72. You multiply this and this, you get a factor of 72. You multiply this and this, you get a factor of 72. And for that matter, any other combination will also yield a factor of 72. Okay, just try and understand what I'm trying to do here. So what I'm doing is take anyone from this, take anyone from this, and you multiply. We already know that the total factors of 72 are 12. We have already, I think, counted earlier. Okay, now you see. So you just take 2 raised to 0 into 3 raised to 0. You take 2 raised to 0 into 3 raised to 1. 2 raised to 0 into 3 raised to 2. Right? Then you take 2 raised to 1 into 3 raised to 0. 2 raised to 1 into 3 raised to 1. These are all factors of 72. 3 square. Then 2 raised to 2 into 3 raised to 0. 2 raised to 2 into 3 raised to 1. Okay? 2 raised to 2 into 3 raised to 2. Then 2 raised to 3 into 3 raised to 0, 2 raised to 3 into 3 raised to 1, 2 raised to 3 into 3 raised to 2. So these are all possible factors. If you can match, this is what? 1, this is 3, this is 9, this is 2, this is 6, this is 18, this is 4, this is 12, this is 36, this is 8, this is 24, this is 72. So these are factors of 72. You can just check the list, earlier list that you had. Now, what we understand from here is, what we need to do is just create combinations of powers of 2 and powers of 3, right? So how many combinations are created? 12 combinations. Now, do we need to do all this every time? No, absolutely no. What you have to do is, you just see 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. 3 to the power 0, 3 to the power 1, 3 to the power 2. Now, if I take 2 to the power 0 with this 1, 2, and 3 combinations can be created how? 2 raised to 0 into 3 raised to 0, 2 raised to 0 into 3 raised to 1, 2 raised to 0 into 3 raised to 2. So for 2 raised to 0, 3 combinations. Similarly, 2 raised to 1, 3 combinations. 2 raised to 2, 3 combinations. 2 raised to 3, 3 combinations. So total 4 into 3, that is 12 combinations. Hence 12 factors. 12 combinations, 12 factors. Right? So from now on, you just need to count how many possible powers of one prime factor, how many possibilities for the powers of the other prime factor, and you just multiply. So 2 ke liye, there are 4 possibilities, 3 ke liye, there are 3 possibilities. You don't even need to write all this, you just count from here. 2 raised to 0 is already, 2 raised to 3 is already there, so start from 2 raised to 3, go downwards, 2 raised to 2, 2 raised to 1, and 2 raised to 0, go up to 0. So 4 possibilities for 2 powers of 2. Similarly, 3 raised to 2 is there, 3 raised to 2, 3 raised to 1, 3 raised to 0. So 3 possibilities for 3. Total 4 into 3, 12 combinations. Right? Let's take for the other numbers. For example, 144. So we don't need to write this. We can simply count on our fingers. 2 raised to 4, 2 raised to 4, 2 raised to 3, 2 raised to 2, 2 raised to 1, 2 raised to 0. So 5 possibilities for this. And for 3, 3 raised to 2, 3 raised to 1, 3 raised to 0. So 3 possibilities for this. Multiply, you will get 15. 5 into 3, that is 15 factors. So there are 15 factors for 144. Say for example 27,000. So 27,000, 2 raised to 3 is already there. 2 raised to 3 plus then 2 raised to 2, 2 raised to 1, 2 raised to 0. There is 4 possibilities for this. Then for 3 raised to 3, again 4 possibilities. 5 raised to 3, again 4 possibilities. So 4 into 4 into 4, which is 64 factors. So that means 27,000 has 64 factors. I hope by now you also understand that you don't need to do any of these things. You just need to factorize, check the powers of prime factors and just plus 1. Add 1 to the powers. Right? So in short, if I remove all this and I just do one thing, look at the power of 2 in this case, let's say in case of 72. Look at the power of 2, it is 3, so 3 plus 1. Power of 3, that is 2 plus 1. And then you multiply, so you will get your number of factors. So that what I just explained was the exact actual process of finding the factors. Now this counting has to be done directly like this, right? So it is 4 into 3, that is 12 factors. Alright, so we actually don't have to do all this. But that was actually a good thing to understand and know about. Okay, so for example, if it was 27,000, what we needed to do was factorize, and after factorization, whatever is the power, add 1 to every power. So it is 3 plus 1 into 3 plus 1 into 3 plus 1. And then you multiply all of them. So which is 4 into 4 into 4, 64 factors. For 144, we don't need to do this, just r plus 1. Okay. How many factors are there for 84,000? Let's see. We already factorized it to be 2 raised to 5, 3 raised to 1, 5 raised to 3, 7 raised to 1. So take all the powers, add 1 to every power. So even power 1 has to be not to be ignored. 3 plus 1 and 1 plus 1. So if you multiply all of them, you get your number of factors. Okay, so it is 6 into 2 into 4 into 2. So 6 to the 12, 48, 96 factors. So I'll just summarize. What you have to do is take the number, factorize it to its prime factors. After factorizing, identify the powers of prime factors, add 1 to every power and then you multiply. Add 1 to every power and you multiply to get your number of factors. Right? So I would say if there is a number n and if it can be factorized like this, let's say prime factors are p1 to the power a, p2 to the power b, p3 to the power c and so on. The number of factors, and make sure that p1, p2, p3 are all prime factors. Okay. number of factors can be given as power plus 1 for each prime factor. Power plus 1 for each prime factor. This will give you your number of factors. Now, let's take some more examples. Let's say 120, 100, 576, 225, 720, 1000, 36,000. So what we have to do is, so you can take a pause and find the number of factors for each one of them and then come back and check. Now 120, if you factorize it to the prime factors, I've already explained the method of factorization. Either this method, 120, you take out common 2, 60, then 2, 30, then 2, 15, and then 3, 5. So we have 1, 2, 3, 2 cube, then 3 to the power 1 into 5 to the power 1, or 12 into 10, and then further 12 can be written as 2 to 3, and 10 can be written as 2 into 5. So total, this comes out to be the factorized form of 120. And then number of factors will be given as number of, so I just write the heading as number of factors. So number of factors for 120 will be powers 3 plus 1, then 1 plus 1, then 1 plus 1. So it is 4 into 2 into 2, which is 16 factors. You can again go back and check for 120, the factors of 120, there are 16 of them. Okay. 100, it is 2 square into 5 square. So the number of factors will be 2 plus 1, then again 2 plus 1, so 3 into 3, 9 factors. 576, it is 24 square. If you remember, it is 2 raised to 6 into 3 square. Now, number of factors will be 6 plus 1 into 2 plus 1. So 7 into 3, which is 21 factors. 2 to 5, it is 15 square. 15 square would mean 3 square into 5 square. So the number of factors will be, powers are 2 and 2. Add 1 to each power. So it becomes 3 into 3. That is 9 factors. So slowly you have to reduce the length of the process. Alright, 720 is 2 to the power 4 into 3 square into 5 to the power 1. Number of factors will be power plus 1, that is 4 plus 1, 5. 2 plus 1, that is 3. 1 plus 1, that is 2. So some mental work if you do, things become a little faster. So 30 factors. Then 1000, it is 2 to the power 3 into 5 to the power 3. That becomes 4 into 4, which is 16 factors. 36,000, it is 6 into 6. Then 10 into 10 into 10, you can see 36 is 6 into 6. Then every 0 will count for 10, 10, 10. So overall 2 to the power 5, then 3 to the power 2 into 5 to the power 3. So the number of factors will be, the powers are 5, 2 and 3. If you add 1 to each one of them, it will become 6 into 3 into 4. So 6 is 18 into 4, 72 factors. Okay, now some observations. One very simple observation is, can you identify the perfect squares out of the numbers that I have given to you? Which one are the perfect squares? 100 is a perfect square, 576 is a perfect square, 225 is a perfect square. These are all perfect squares. And earlier we had done 144, that was 2 to the power 4 into 3 square, and the number of factors was 5 into 3, that was 15 factors. What is one thing common about this? About all of them? 144, 100, 576, 225. If you see the number of factors for each one of them is an odd number. So number of factors for each one of them is an odd number. There is another thing that you can notice. For a perfect square, when you factorize, the powers will always be even numbers. Check for any perfect square. If you factorize a perfect square, the powers will always be even number. We don't do anything, it automatically happens by virtue of the property of numbers. Okay. So just understand that it's like for any number which is a perfect square, if it can be factorized like this, p to the power 2, something to the power 2. So if p can be further factorized, in any case each prime factor here will have a power which will be a multiple of 2, hence even number. Now when you add 1 to each of those powers, each of those values after adding 1 will become odd. Any even number, when 1 is added, each of them becomes odd. Now when you multiply odd numbers, the outcome will always be an odd number. Hence the number of factors will always be odd. So I just write a statement for a perfect square. For a perfect square, the number of factors is always odd. Please understand this thing. Number of factors is always odd. Alright? Now here there is one thing that I need to mention, vice versa. Now what does it mean? If there is a number which is a perfect square, the number of factors will be odd. Similarly, if a number has odd number of factors, it has to be a perfect square. That is one way to look at it. The other way is, if there is a number which is not a perfect square, like say 120, 720, 1000, 36,000, these are not perfect squares. So now if the number is not perfect square, the number of factors will always be even, as we can see, 16, 72, and so on. Okay, so I repeat. For a perfect square, the number of factors is always odd number. And for a non-perfect square, the number of factors is always even, and vice versa. So if I give you a question, listen very carefully. If I give you a question like this, a number has 25 factors. I just say one simple statement. A number has 25 factors. What is the inference that you can take out from that? At least one information that you can take out from there is, I'll first write the statement. A number n has 25 factors. Can you tell me anything about that number n? There is at least one thing that you can say. What? The number of factors is 25. 25 means odd, so it has to be a perfect square. That means n is definitely a perfect square. What perfect square? That we don't know. But at least we can say that it has to be a perfect square. That's what I mean to say. Similarly, if I say a number p has, let's say, 52 factors. What is that one thing that you can definitely say about this number? You can definitely say that it is not a perfect square. Why? Because if it was a perfect square, the number of factors should have been odd. If for non-perfect square, the number of factors is even. So here the number of factors is even, hence P is definitely a non-perfect square. That is for sure. The question can be something like this. For this one, the question can be root n can be, and there will be 4 options. So you will say it will be a rational number, right? Because if it is a perfect square, the square root will exist, right? Here, root of p will be an irrational number. The options will be irrational, rational, everything will be there. You have to mark, because p is not a perfect square, so root p will be an irrational number. That is how you need to look at them. Let's take up a question. Find sum of factors of 72. Okay. Now suppose it is, we already have factorized 72 and that was 2 cube into 3 square. Now just to recall, how did we find the number of factors? What we said was, the possible powers of 2 which can create factors of 72 are 2 raised to 0, 2 raised to 1, 2 raised to 2 and 2 raised to 3. Similarly, the possible powers of 3 to create a factor of 72 were 3 raised to 0, 3 raised to 1 and 3 raised to 2. Alright? And we just multiplied the number of possible combinations to find number of factors. Now to find sum of factors, see what we have to do. Sum of factors, what we do, we simply add them. Sum of factors would be equal to, let's see, add all the possible powers of 2. So 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3. Multiply it by all the possible sum of possible powers of 3. So that is 3 raised to 0, 3 raised to 1 plus 3 raised to 2. So that will give us 1 plus 2 plus 4 plus 8 into 1 plus 3 plus 9. Now this is 8 plus 4, 12 plus 2, 14 plus 1, 15 into 13, which is 195. That is the sum. So if you add those 12 factors of 72, the total sum will be 195. You can actually check it, right? Now, how does this happen? Do you remember the process of formation of factors? I'll just recall you once more. 2 raised to 0 into 3 raised to 0 was the first factor. 2 raised to 0 into 3 raised to 1 was the second factor. 2 raised to 0 into 3 raised to 2 is the third factor. Then 2 raised to 1 into 3 raised to 0, 2 raised to 1 into 3 raised to 1, 2 raised to 1 into 3 raised to 2. These were the next set of factors. 2 raised to 2 into 3 raised to 0, 2 raised to 2 into 3 raised to 1, 2 raised to 2 into 3 raised to 2. The next set of factors. 2 raised to 3 into 3 raised to 0, 2 raised to 3 into 3 raised to 1, 2 raised to 3 into 3 raised to 2. These are all possible factors of 72. We have to add all of them. Now let's do one thing. Add these three. What will you get? 2 raised to 0 into 3 raised to 0 plus 3 raised to 1 plus 3 raised to 2. Now add these three. You will get 2 raised to 1 into the same thing. 3 raised to 0 plus 3 raised to 1 plus 3 raised to 2. In these 3, again the sum will be same. 2 square into 3 raised to 0 plus 3 raised to 1 plus 3 raised to 2. In these 3, also the sum will be 2 cube into 3 raised to 0 plus 3 raised to 1 plus 3 raised to 2. Now if you add all of these, what will happen? You will get 3 raised to 0 plus 3 raised to 1 plus 3 raised to common. And the other things would be 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3. Which is nothing but the sum of all possible powers of 2 and all possible powers of 3. So you don't have to get into the details of this, you can directly do this. Right? Okay. So in general, if I have to write like this, if there is a number n, which can be factorized in a form of prime factors like this, p1 raised to the power a into p2 raised to the power b into p3 raised to the power c and so on, the sum of factors of n is equal to, what do we have to do? For let's say p1, you start from the first power of p1, that is p1 raised to 0, p1 raised to 1, go on up to the given power of p1, add all of them, multiply it by p2 raised to 0 plus p2 raised to 1 plus p2 raised to 2, go up to, let's say, p2 to the power b, and do it for every other factor. p3 raised to 0, p3 raised to 1, p3 raised to 2, goes up to p3 raised to c, and so on. As many prime factors are there. The number of parts here will be as many prime factors are there for the number n, and so on. Okay. So for example, if I have, let's say, 100. So sum of factors of 100. So first we factorize 100, we get 2 square into 5 square. So sum of factors would be equal to 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 into 5 raised to 0 plus 5 raised to 1 plus 5 raised to 2. And you multiply them, so you get 1 plus 2 plus 4. Then you get into 1 plus 5 plus 25. So you have 4 plus 2, 7, 6 plus 1, 7 into 31. So it is 217 is the sum of factors. Let's say for 120. 120 is 2 cube into 3 to the power 1 into 5 to the power 1. So we have sum of factors that can be taken as 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3 into 3 raised to 0 plus 3 raised to 1 into 5 raised to 0 plus 5 raised to 1. This will come out to be 1 plus 2 plus 4 plus 8. If you do a practice, it is directly 15 into 3 plus 1, that is 4, into 5 plus 1, that is 6, and this is 360. So the sum of factors of 120 is 360. Just one simple addition that I would like to do here. If you look at this carefully, if you are aware about something called geometric progression, this series is a geometric progression. This is another geometric progression. This is another geometric progression. And for geometric progression, there is a direct formula also. I'll just give that separately. The geometric progression usually looks like this. Look at this. AR squared, let's say up to AR n minus 1. The nth term expression is AR n minus 1. Okay. Now, this is geometric progression, right? So, if you have done geometric progression, if you are aware about them, you can use this formula. How? This sum is equal to, let's say sum of n terms is equal to A into R to the power n minus 1 upon R minus 1. Okay. This is the formula if R is greater than 1. In our cases, R will always be greater than 1 because we will be taking prime factors. Okay. Now, in this case, if you see p raised to 0, p raised to 1 and so on. So, the first term, here the first term is a. Here in each case, the first term will be 1. So, that is removed. So, I'll put another thing. If a is 1, then sum of n terms will be simply r raised to n minus 1 upon r minus 1. R is what? R is the common ratio. So the number by which it is getting multiplied. So AR square and so on. In this case it is P1, then P1 is to 0, then P1 is to 1, then P1 is to 2. That means P1 is getting multiplied. In this case P2 raised to 0, P2 raised to 1. If you take an example, here it was 2 raised to 3. So 2 raised to 0, then 2 multiplied, then again 2 multiplied, then again 2 multiplied. So in this case the common ratio is 2. In this case the common ratio is 3. In this case the common ratio is 5. Okay. So if this is the situation, I'll read it out for you once again. Sum of n terms is r to the power n, okay, minus 1 divided by r minus 1. Right? So the sum of factors can be written as, I'll just remove this for a moment. It can be written as P1 raised to the power, this is a plus 1 terms. Alright, so it is P1 raised to the power a plus 1 divided by P1 minus 1 into P2 raised to the power b plus 1 minus 1 upon P2 minus 1 into P3 raised to the power c plus 1 minus 1 upon P3 minus 1 and so on. So this is another way, but I would recommend not to use this unless you have done geometric progression properly. Alright, just check it very carefully. For example, in this case, because I have given you the formula in one or two questions, we'll use it also. It is how many terms? 1, 2, 3, 4 and common ratio is 2, right? So here the power was 3, so 3 plus 1 minus 1 upon 2 minus 1 into, this is 3 to the power is 2, so 2 plus 1, or you could also say it is just the total number of possibilities, right? Minus 1 divided by 3 minus 1. So if you calculate, it comes out to be 2 to the power 4 minus 1 upon 1 into 3 to the power 3 minus 1 upon 2. So this comes out to be 2 to the power 4 is 16 minus 1, 15 into 3 to the power 3 is 27 minus 1 upon 2. So it is 26 by 2, that is 13. So 15 into 13, 195. The answer would be same. So as I said, if you are aware about geometric progression, then only you should think about this formula. Otherwise, the previous explanation is just fine. It works really well. Okay. Now, what I'll do is I'll give you certain more examples. Let's say find the sum of factors of 600, sum of factors of 720. Question is find sum of factors. Find sum of factors of 28, sum of factors of 6. So you can pause and you can find the sum of factors of these numbers. I'll give you one more number, 1000. Okay. Now 600 can be 2 cube into 3 square, 3 raised to the power 1 into 5 raised to the power 2. Sum of factors can be taken as, from here only I'll put the heading as sum of factors. So I'll follow without geometric progression. Here it will be 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3. And I'm sure by now you should understand that you don't need to write this. You can do this mentally and put the values here. Into 3 raised to 0 plus 3 raised to 1 into 5 raised to 0 plus 5 raised to 1 plus 5 raised to 2. So this is 8 plus 4, 12 plus 2, 14 plus 1, that is 15 into, this is 3 plus 1, 4 into, this is 25 plus 5, 30 plus 1, 31. So it is 60 into 31, that is 1860. That is the sum of all factors of 600. How many of them? You can actually check. How many factors will be there? 4 into 2 into 3. So 4 into 2 into 3 is 24 factors. So that means the sum of 24 factors of 600 is 1860. That means if I list down all the factors of 600 and I add them, the total sum will be 1860. 720, if you factorize, you get 2 to the power 4 into 3 square into 5 to the power 1. Number of factors will be what? 5 into 3 into 2. That means 30 factors. So I'll repeat. The sum of those 30 factors of 720 will be this much. How much? You can with practice you can simply add, without writing you can add 2 raised to 4. That means 16, then plus 8, lower power, that is 24, plus 4, that is 28, plus 2, 30, plus 1, 31. So it is 2 raised to 0, plus 2 raised to 1, plus 2 raised to 2, plus 2 raised to 3, plus 2 raised to 4. You can also see, especially for 2, the sum of powers is simply the next power minus 1. For example, here, we had 3 powers. So next power would be 2 raised to 4, that is 16 minus 1, 15. But that will not happen for others, right? It is exactly the same formula. But yeah, you can shorten for at least for powers of 2. But don't use it for others because you always have smaller powers. So nothing to worry as such. 3 raised to 0 plus 3 raised to 1 plus 3 raised to 2 into 5 raised to 0 plus 5 raised to 1. Now this will be 16 plus 8, 24 plus 4, 28 plus 2, 30 plus 1, 31 into 9 plus 3, 12 plus 1, 13 into 5 plus 1, that is 6. So it is 31 into 78. Right? That if you multiply, it will be 2418. Do the multiplication on your own. 28. 28 is what? 2 square into 7 raised to 1. So I directly find the sum of factors. 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 into 7 raised to 0 plus 7 raised to 1. So it is 4 plus 2 plus 1, that is 4 plus 2 6 plus 1 7 into 8, which is 56. 6 is 2 to the power 1 into 3 to the power 1. We already know that the factors of 6 are 1, 2, 3, 6. You can actually add them. That sum will be 12. Let's check from the formula. 2 raised to 0 plus 2 raised to 1 into 3 raised to 0 plus 3 raised to 1, which is 2 plus 1, 3. 3 plus 1, which is 4. So 3 into 4, that is 12. Sum of factors of 1000. It is 2 to the power 3 into 3 to the power 5 to the power 3. So the sum of factors will be 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 into 5 to the power 0 plus 5 to the power 1 plus 5 to the power 2 plus 5 to the power 3, which is 8, 4, 12 and 1, 15. 14 and 1, 15 into 125, 25, 150, 155, 156. Multiply this, 2250 plus 90, 2340. This is the sum of factors of 1000. That means, 4 into 4, 16 factors of 1000. If we add them, the total sum will be 2340. Now here there are some specific numbers. Yeah, so this is how we can find the sum of factors. Now see, look at 28, 6. For them, the sum of factor is exactly twice the given number. 28, 56, 6, 12. There is another number. Let's say 496. Can you find the number of factors of 496? Check it. 496, if you find the number of factors of this number, let's see. First you need to factorize this. If you factorize it is 4 into 124. So 2 raised to 4 into 31 raised to 1. 2 raised to 4 into 31 raised to 1. And we need to factorize this by that Ganda method. Take out 2, you get 248. You could have taken out 4 directly. So take out 2, you get 124. Again, you can take out 2, you get 62. Again, you can take 2, you get 31. 31 is not factorizable. So it is 2 raised to 4 into 31 raised to 1. The sum of factors for this will be 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus 2 raised to 3 plus 2 raised to 4 into, then for 31 you will have 31 raised to 0 plus 31 raised to 1. That will be equal to, the sum of this will be 31 into the sum of this will be 32. If you multiply, you get 992. If you look at this closely, 992 is just double of 496. Yes, exactly, because this was 16 into 31 and this is 32 into 31. So sum of factors of 496 is exactly double of 496. The set of these numbers for which the sum of factors is double the number, there has been a name that is given to them, and that name is perfect numbers. Alright, so let's say perfect numbers. You can note down perfect numbers, the numbers for which the sum of all factors is twice the number. How many factors of 84,000 are divisible by 10? So for example, the first thing that you need to do is factorize 84,000. That is 2 to the power 5 into 3 to the power 1 into 5 to the power 3 into 7 to the power 1. When we have to find the total number of factors, we had already done it. that is number of factors would be equal to 6 into 2 into 4 into 2. 96 factors. The question is, out of these 96 factors, how many are divisible by 10? How to do it? I'll explain it to you very simply. One very simple thing is, what do we need to do? We need to get numbers which are divisible by 10. So what you have to do is, divide the given number by the required number. So 10 is the required number, so divide by 10. What do we get? 8400. Just count the number of factors of 8400. That will be the answer. So 8400 will be what? 8400 will become, now what we are doing is we are dividing this number by 10. That means this also will get divided by 10. That means 10 is what? 2 into 5. So 1, 2. The power of 2 will reduce by 1. So 2 raised to 4. 3 will remain same. The power of 5 will also reduce by 1. And 7 will remain same. Or you can start factorize 8400 separately. I'll explain 84,000 by 10. That means this whole thing divide by 10. Now 10 itself is 2 into 5. So the power of 2 will reduce by 1. Power of 5 will reduce by 1. The rest everything will remain same. Now this is 8400. Number of factors of 8400 will be 5 into 2 into 3 into 2. That is 60. So what we have done? We have already ensured 10. Right? And then the number of factors is 60. This 60 must be out of the 96 factors, because one thing is very clear. Any factor of 8400 will also be a factor of 84,000. Right? Now these 60 factors will also be the answer of this question. Okay. So what we need to do, we just need to ensure that the number is divisible by, or the factor is divisible by 10. So what we have to do, the method is divide the given number by the divisible by whatever number it is. Okay. You get a new number, find the number of factors of this. This will be the answer of that question. So we can say that out of 96 factors of 84,000, 60 factors are divisible by 10. This is what we can say. So out of 96 factors of 84,000, 60 factors are divisible by 10. Okay, let's take other examples. How many of them are, let's say, for the same number 84,000, how many are divisible by 4? Divisible by 4. What do we have to do? 84,000 divide by 4, which is 21,000. Find the number of factors of 21,000 will be the answer of this question. Okay, so 21,000 will be 2 to the power. Now, the 4 is 2 square. So the power of 2 will reduce by 2. So it becomes 3. 2 to the power 3 into remaining other things will remain exactly the same. So this number of factors for this will be 4 into 2 into 4 into 2. That is 8 into 8, 64. So 64 factors. What does it mean? Out of 96 factors of 84,000, 64 are divisible by 4. Alright, let's take another situation. Divisible by 84. So 84,000 divide by 84. This will be 1,000. 1,000 means 2 cube into 5 cube. So it is 4 into 4, that is 16 factors. So what does it mean? Out of those 96 factors, 16 factors are divisible by 84. How many factors are divisible by 7? So 84,000 divided by 7. We get 12,000. We get 12,000, factorize 12,000 and find the number of factors. It will be 2 to the power 2 and 3, 5, 3 to the power 1, 5 to the power 3. Or from there we could have seen this only 7 will get cancelled out, remaining things will remain exactly the same. So the number of factors of this will be 6 into 2 into 4. That is 48 factors. That means out of those 96 factors, half of them, 48 are divisible by 7. Fourth one, how many factors of 84,000 are even? How many factors of 84,000 are even? How do you understand the question? The factors have to be even, like 2, 4, 6, 8, 10, 12, 14 and so on. So how many factors of 84,000? So out of these 96 factors, how many are even? This is what we have to find. Now we also know that even numbers are actually what? Divisible by 2. Alright, so whatever we have done till now, the same method can be applied. Divisible by 4, divisible by 84, divisible by 7, similarly divisible by 2. So what do we have to do? 84,000 divided by 2, so it is 42,000. Or the factorized form of 84,000, if you divide it by 2, the power of 2 will reduce by 1, that's it. So 2 to the power 4, remaining things will remain as it is. 3 raised to 1, 5 raised to 3, into 7 raised to 1. So the number of factors will be 5 into 2 into 4 into 2. So it is 10 into 4, 40 into 2, 80. What does it mean? Out of 96 factors, 80 factors of 84,000 are even. Hence, if the question was, how many? Okay, so I just summarize this. Number of factors which are even, what do you have to do? Just divide the given number by 2. That's it. Nothing else has to be done. Find the number of factors of the new number. You will get your required answer. Okay. Now, if I say how many factors of 84,000 are odd. So, I'm sure you can find it is 96 minus 80, so 16 factors. Because the number has to be either even or odd. The total number of factors is 96. Out of them, 80 are even. So 16 will be odd. Okay? So that you can already do. It is 16 factors. But there is a direct way also. What do you have to do? Divide or let's say factorize 84,000. That is 2 to the power 5 into 3 to the power 1 into 5 to the power 3 into 7 to the power 1. Okay? Now, how is a factor formed? The factor is formed by power combinations of 2, 3, 5, 7 in this case. Right? If I do not take the power of 2, any power of 2, automatically the number will be formed or the factor will be formed with the help of 3, 5 and 7. Now all these 3, 5, 7, they are all odd numbers. So any combination of those factors will result in an odd factor. As simple as that. Okay, so what we have to do, if you have to find the number of factors which are odd, just factorize the number and ignore the power of 2 completely. And then find the number of factors from the remaining portion. So the number of factors from the remaining portion will be the same method. The power is 1, so 1 plus 1 is 2. Power is 3, so 3 plus 1 is 4. Power is 1, so 1 plus 1 is 2. So 2 into 4 into 2, that is 16 factors. So this is the direct way of finding. Because in the exam, you may not have both the questions. There will be just one question. So number of factors which are odd, how will you find it? Factorize, remove the powers of 2. Completely remove the powers of 2. Then find the number of factors for the remaining portion. All those factors will be odd. So, sixth question. How many factors of 84,000 are perfect squares? Again, factorize 84,000. What do we have? 84,000 is 2 raised to 5 into 3 raised to 1 into 5 raised to 3 into 7 raised to 1. In some of one of the previous examples, we had actually discussed that any square will look like this. Let's say n is equal to p square. So even if we factorize p, let's say p1 into p2 into p3, and suppose it is power a, b, c and so on, and power 2. Effectively what will happen? p1 to the power 2a into p2 to the power 2a into p3 2b, sorry, and p3 to the power 2c and so on. So even if you factorize, the powers of the prime factors still have to be even numbers. Alright? Now here, come back. We want our factors which are perfect squares. Okay? So what do we have to do? Here, what are the possible powers of 2? 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5. What are the powers of 3? 3 raised to 0, 3 raised to 1. What are the powers of 5? 5 raised to 0, 5 raised to 1, 5 raised to 2, 5 raised to 3. What are the powers of 7? 7 raised to 0, 7 raised to 1. Now see, I want to create a factor, let's say factor which has a power of 2, which has a power of 3, which has a power of 5, which has a power of 7. Let's say x, y, z, t. But I want this factor to be a perfect square. So if I want this factor to be a perfect square, each of these prime factors should have a power which is only even number. Okay? Should have a power which is only even number. Right? So now we will not count all possibilities of 2, 3, 5 and 7. Right? Now what do? We just go back and check the powers of 2 and pick up those possibilities in which the power of 2 is an even number, like this one, 2 raised to 0, 2 raised to 2, 2 raised to 4. So we have only 3 possibilities for 2. Similarly, in the powers of 3, there is only one possibility. In the powers of 7 or 5 there are 2 possibilities, and in the powers of 7 there is only 1 possibility. So multiply them, 3 into 1 into 2 into 1, and that is 6 factors. Oh, so that means that out of those 96 factors of 84,000, 6 factors are perfect squares. I'll repeat. To find a factor which is a perfect square, you need to take only those possibilities of prime factors which are even power of prime factors. Okay. So even power of prime factors, as in यहाँ पे we have 2 to the power 5. So the possibilities of powers of 2 will be these 6. But out of them only 2 raised to 0, 2 raised to 2, 2 raised to 4. They are even powers. So we consider them 3 possibilities. But for 3, there are only 2 possibilities, 3 raised to 0 and 3 raised to 1. But out of that, only 3 raised to 0 will suit the criteria of perfect square, so only 1 possibility for 3. Similarly, for 5, there are total 4 possibilities, but out of them, only 2 are even power possibilities. So 2 possibilities. For 7, there is only 1 possibility. So we have 3 into 1 into 2 into 1, that is 6 factors. I hope you understand this. Okay? Alright. Now, we will take new concept, that is co-prime numbers. Let's see. We all know about prime numbers, right? Now, prime numbers is a standalone criteria or a category of numbers. The numbers which have exactly 2 factors. One and itself, that we have already done. Now, let's talk about co-prime numbers. First of all, the part co means what? Together. Cooperation, cooperative, and so on. Now here, what do we mean by co-prime? So first of all, we need to understand that co-prime is always a pair of numbers, right? Co-prime is not a standalone criteria, okay? Co-prime numbers means, let's say if there is a pair of numbers which does not have any common factor. Now, when I say it does not have any common factor, please understand, 1 is the factor of every number, okay? So 1 will always be a common factor of any pair of numbers. So what we are saying here is, if 2 numbers do not have any common factor other than 1, then they are called co-prime numbers. Right? I'll take an example first. So let's say 24 and 25. Please see that both are non-prime numbers, both are composite numbers. But if you look at the common factor, there is only one common factor, and that is 1. Hence, these are co-prime numbers to each other. So co-prime numbers will always exist in pairs or in groups. Alright? So 2 numbers are said to be co-prime, always pairs. So 2 numbers are said to be co-prime to each other. It cannot be standalone co-prime. It always has to be co-prime to each other. If they have only one common factor. And the common factor obviously has to be 1. Common factor 1. See, and that 1 will automatically be a common factor, right? So you don't have to think anything else. If other than 1, even if there is one common factor, then they are not co-prime to each other. Alright? In simpler words, we can simply say if HCF of 2 numbers A and B is equal to 1. We'll study about HCF in little more detail in a little while. HCF is highest common factor. So if HCF of 2 numbers is 1, then A and B are said to be co-prime to each other. A and B are co-prime to each other. That's what it means. Alright. Now, let's take some more questions related to factors and their presentation as products. Question is, in how many ways a natural number n can be presented as a product of 2 natural numbers. Alright. And now we'll take different values of n. Alright. So first question, let's say if n is 100. Or not 100, let's take smaller number, 72. So in how many ways a natural number can be presented as a product of 2 natural numbers? Let's take the actual situation. 72 can be written as 1 into 72. 2 into 36. The similar process we have already done in the past. 3 into 24. 4 into 18. 5 will not be a factor. 6 will be a factor. 6 into 12. 7 will not be a factor. 8 into 9. Further, we don't need to go. Okay. So 1, 2, 3, 4, 5, 6. So just there are 6 pairs. So the answer to that question will be 6 ways. Alright, so the answer is 6. Yeah, right. We did this earlier also to find number of factors. Right? The total number of factors was what? This is 2 cube into 3 square. So total number of factors was 4 into 3, 12 factors. So if there are 12 factors, automatically there will be 6 pairs. How? In every pair, 2 factors will be utilized. And there are a total of 12 factors. So how many pairs can be created? Unique pairs will be 12. Divide by 2. Right? So the answer of this question is always equal to half of number of factors. Okay, you can check for any other number. Right? So if I take a second example, so product of two natural numbers, the answer is simply half of number of factors. But there is a catch here, we'll come to that also. Okay, let's take some more numbers. If I have, simply n is equal to 720. So 720 is what? 720 is 2 to the power 4, 3 to the power 2, 5 to the power 1. So there will be 5 into 3 into 2. That is 30 factors. Okay. 30 factors. That means the answer to that question will be simply 15 ways. You have 15 pairs. Why? That number of pairs will be number of pairs. That is the question asking how many ways we can write. That means we are asking the number of pairs is equal to half into 30. That means 15 pairs. Alright. Now, for this particular situation here, I will write all possibilities. Okay. Will not use that. That is not required also. But just for the better understanding, I write all possibilities. So 720 is equal to what? 1 into 720. 2 into 360. 3 into 240. Right? 4 into 180, 5 into 144, 6 into 120, 7 will not be there, 8 into 90, 9 into 80, 10 into 72. You can see that this will go on increasing, this will go on decreasing. 11 will not happen, 12 into 60, then 13 will not happen, 14 will not happen, 15 into 48, 16 into 45. Okay, so if you have already factorized, it will help. 17 will not be there, 18 into I think 40, yes, 19 will not be there, 20 into 36, and then 24 into 30. Have I missed anyone? You can check. I don't think so. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. These are the actual 15 pairs. After this, it will repeat 13 to 24. So you shouldn't repeat. So total number of possible pairs is 15 in this case for 720. So this is how things will happen. So if you go on actual counting, you may not be able to get all the pairs first of all. You may make some mistakes, so better is to follow that process, the method. That's it. Simply half of number of factors. Alright. So it is simply half of number of factors. But if I take, let's say, third one, n equal to 100. Now what is so specific about 100? So for 100 also, we'll take all possibilities. So 100 can be written as 1 into 100, 2 into 50, 3 will not happen, 4 into 25, 5 into 20, and in the end, 10 into 10. Now this 100 was 2 square into 5 square, so we know it is a perfect square. So number of factors we would have calculated like this, 3 into 3, there are 9 factors. Oh. In fact, for all the perfect squares, the number of factors will always be odd. This we have seen in the past. In the earlier session, we have seen that for all the perfect squares, the number of factors will be odd. Now, if I follow this method, half of number of factors, so half of 9 will be equal to 4.5. Now, there cannot be 4.5 pairs. I mean, you can't have a half pair. So, why does it happen? What should we do? Here it says 5 pairs. From that method, we are getting 4.5 pairs. There is some problem with this. Actually, the problem can be resolved very clearly. You come back to this, it says a two natural number. Does it say two distinct natural number? No. Did we face that problem here in this, which was not a perfect square? No. Alright, so first of all, this problem will happen only for perfect squares. Why? Because for non-perfect squares, the number of factors is even. So when you divide it by 2, it gives you a full number, an integer. But when it is for a perfect square, the number of factors is odd and it gives you a decimal number. So that is not possible. So this problem will happen only for a perfect square, first of all. Alright? Then there will be two categories, two things that we need to do. One, we go back to this and we say, I am removing this. I am removing this so that I can write in detail. The first thing, it is, so in how many ways a natural number n can be presented as a product of two natural numbers? The answer is half into number of factors for non-perfect squares. Okay? And for perfect squares, we'll have two cases. How? For perfect squares, the same statement, I'm using the same statement here, and from here of two natural numbers. Of two natural numbers. What do we do? Number of factors plus 1 by 2. And if I put the same thing again here, like in how many ways a natural number can be presented as a product of two distinct natural numbers. Natural numbers. So that will become number of factors minus 1 by 2. Alright? Yeah, this is just to mention. But do we need to really memorize this and so on? I don't think so. If you just look at this, what is happening? Always for a perfect square, there will be one pair in which both the factors will be same. The other pairs will not have any trouble. Right? So this 4 does not have a trouble, absolutely. So 4 will definitely be a part of the answer. So if the question simply says, that the product of two natural numbers, then answer will be 4 plus this one, right? And if the question says that of two distinct natural numbers, so this thing where the numbers are same will not be considered, answer will be only this 4. I hope that this makes sense. I'll repeat. Here, the actual number of pairs is 5. Without doing this, we already had an answer which was 4.5. Now 4.5 is not possible answer because the number of pairs cannot be fraction. But the integer part of that is 4. That 4, so what it means is 4 full pairs and 1 half pair. That's what it means. The number of full pairs will be there definitely, for sure. So if the question says product of two numbers, then just take the valid possibility out of this, plus 1, that is 5. The valid possibility out of this, plus 1. Remember, valid possibility, we have already talked about it. What? If there are 4.5 pairs or numbers or items, what is the valid possibility? 4, the lower side integer. And then 1 for that possibility in which both the factors are equal. Always this will happen. 4 plus 1 and 5. But if it says product of two distinct numbers, then what do? We do not consider that last pair jo equal wala tha, so it is just 4 is the answer. So whenever there is a number which is perfect square, only then this problem will arise. So you actually don't have to memorize this formula. It will just likhne ke liye diya. You can do it directly also. Okay? Let's take some more examples. Otherwise, if you have used the formula, what will you see? Number of factors 9 plus 1, 10 upon 2, that is 5 pairs. And number of factors 9 minus 1, that is 8 divided by 2, 4 pairs. This problem, again I repeat, it will happen only for perfect squares. So let's take, if we have a number as 144, n is 144. So 144 is what? 2 to the power 4 into 3 to the power 2. Alright, so number of factors will be 5 into 3, that is 15 factors. Right, now 15 by 2, that is equal to 7.5. So what do we know? If it says product of two distinct natural numbers. So what would how would the question read? It would read, in how many ways 144 can be presented as a product of two distinct natural numbers? Listen again. In how many ways 144 can be presented as a product of two distinct natural numbers? Right? Now, if it is distinct, then what do we have to do? We do not have to consider the extra pair. Just the 7 will be the answer. I changed the order. Be careful. Product of two distinct natural numbers, just 7. But if it says simply the product of two natural numbers, distinct word is not there. Product of two natural numbers. Then what will happen? The answer would be these 7 plus that one pair in which both the numbers are equal, that is 12 into 12. Alright? Okay. So this is how we can do this. Let's take another example. If it is 5 n equal to 900. So the question would read, in how many ways 900 can be presented as the product of two distinct natural numbers and product of two natural numbers. Okay. So it is, number is equal to 900. So 900 is what? 30 square. So 2 square into 3 square into 5 square. So if I say number of pairs for product of two distinct natural numbers. Distinct natural numbers. What will be the answer? This number of factors will be 3 into 3 into 3. That is 27 factors. Alright, so the number of pairs will be 27 and a half. 27 and a half, that is 13.5. Now distinct is required, so 13, the lower side. 13 pairs. Okay. And if the question says product of two natural numbers, simply the natural numbers, the distinct is not there, that means the last pair has to be considered. Okay, and the last pair was actually 30 into 30. So with these 13 pairs, one more pair, that is 14 pairs. So the answer is 14 pairs in this case. So just be careful about the language of the question. Alright, so this is done.